Hello, welcome to Chapter 7. We're working in Section 6 where we're going to be talking about adding and subtracting polynomials. In this first example, we're going to be adding and subtracting the monomials, which are just the individual terms of the polynomial. Now, one of the things that we math teachers do is we introduce ideas, and I don't really know if we do a very good job of explaining what those ideas are. And this is one of those examples, and you've heard me talk a couple other times about this. This is one of those examples. So what we do is we say we want to add or subtract. We have to add or subtract what we call like terms. And we often say, okay, we're going to add like terms. We're going to subtract like terms, combine like terms. And then students will say, well, what does that mean? Or actually, what happens most of the time, students don't even ask because they think I should know what that means. Well, this is like, it's just a name for something. That's all that it is. Well, what does it actually mean? Well, like terms, and I'll give you the book definition, but then I'm going to explain it. They have the same variable. So if I look at my examples that you see, my variable here is m, over here I'm using x, down here I'm using y, and over here I've got x and y. So like terms have the same variable. I can't add x's to m's or x's to y's or anything else. Each of those letters that's being used to take the place of a variable is unique. Of course, that doesn't really help much, does it? The other part of the book definition is that they have the same exponent or power. So not only can I only add x's to x's, but I cannot add x to x squared, or x to the fourth power to x to the seventh power. All right, so that's what we say. We say that's the definition, you should know it. And of course, that gets really, really frustrating because algebra is a language, and just saying, well, this is the way we do it, that's not good enough for someone like me. I need to know why. So I'm going to come back to that paper. I'm going to try to explain. One of the cool things that we can do that is really, really, really powerful while you're learning algebra is a symbolic language, which means we use symbols. Okay, and actually a lot of things are symbolic language. The letters that you know, A, B, C, D, E, F, G, those are symbols. Those are symbols for sounds. We can also use symbols in other ways, like as we learn new ways to communicate, like for example, learning shortcuts in texting or shortcuts in electronic communication, we pick up symbols. Well, algebra is a symbolic language. But there's a way of connecting algebra with geometry. Geometry is the study of like two-dimensional and three-dimensional figures. And connecting algebra and geometry was one of the biggest ideas that happened in pushing math forward. And this video is not enough for me to like get into that, but we see it in all different types of places. And actually sometimes we get so used to it that we don't even realize that it's happening. But this is one of the cases where it's good for us to be able to think about what's really happening. So I'm going to try to explain what's happening here. So let's talk about the number 1. All right, I'll even do it with the serifs. The number 1. We all know what number 1 is, okay? This is one marker. All right. What else do I have on my desk? Okay, this is one calculator. All right, I've got one piece of paper here. We know what number 1 is. Well, I can draw number 1 geometrically. Geometrically, this marker I might have to change. I can draw it as a square, and if I measure the distance of the side, if I say this is just 1 unit, and if I say this is 1 unit, then the area is going to be 1 square unit, whatever that is. So again, we just use unit because it doesn't matter whether it's an inch, a mile, a foot, whatever. Okay, or some other unit of measurement that we're not even used to. It just says the distance from here to here is 1, from here to here is 1, 1 times 1 equals 1. That's the geometry part of it, finding the area. All right, and actually I should say area here. All right, I'm gonna grab another marker. I think that one's at its end. I have to see if I got another one nearby. All right. So now let's pick like another number. I'm just gonna pick it small because I don't want to draw too much. So let's pick the number 5. Well, what does 5 look like? Well, we know 5 is 1 plus 1 plus 1 plus 1 plus 1. So I can actually draw it 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The number 5 looks like this rectangle where it's 1 times 5, and the area of this rectangle, again, we're getting to algebra. I know this is not algebra yet, but we're getting algebra. So numbers can be represented by geometric shapes. And the area is going to be 1 times 5, which equals 5. All right, now here's where the algebra comes in. What is x? Well, remember, x stands for a number or a measurement that we don't know. It's just a placeholder. That's all that it is. A lot of what we do is trying to find out what actually is represented by the x. A lot of what we do is abstract, where the x is just, kind of like there. But that's probably a bad way of saying it. But the important thing to remember is that x just represents a number, a measurement, something that we can count. And 1 and 5 are nice numbers. What I mean by nice numbers is that they're numbers that we learn about in kindergarten, okay? They're counting numbers. X is a little bit more complicated. It doesn't have to be a whole number, a counting number. Those are actually called natural numbers, excuse me. It could be a decimal, it can be a fraction, it doesn't matter. All I know is that it stands for a number which I don't know what the number actually is. So how does that look as a rectangle? Well, it's still going to be 1, and then I'm going to draw my rectangle this way. Now I know that I'm not drawing it too big. I know you're probably thinking, well, it's 6. Okay, but here's the deal. This stretches. It's very stretchy, which means that I can pull it to make it as long as I need or shrink it to make it as short as I need. That's the imagination part of it. So just like from here to here was 5, from here to here, I don't know what it is. It's x. And this rectangle represents the variable x. So the area is 1 times x, which equals x. I had to be careful I didn't do an x for multiplying, or that would look really confusing. So if you think about things geometrically, whenever I see an x, I just think of it as a rectangle that is 1 unit wide, but x units long. And if I, just like up here, when I went from 1 square to 5 squares to represent 5, if I had, for example, like let's say 3x. 3x would look like this. So this is still x, and here's 1x, here's 2x, and then here's 3x. So this would be 3, and the area of this one would be 3x. So that's how we get to the idea of like coefficients. Okay, that's probably good. Rewind it if you need me to, if you need to hear it again. If you need me to say it again, rewind it. What about x to the second power though? Well, again, we say x squared. That's because we're going to deal with a square. So this distance is still that x, whatever that number is. So from here to here, from here to here, from here to here, still got that. But now I'm going to go this distance, the same thing. And just like the 1, the area of this one is x to the second power. So we have this idea. We've got 3 different shapes here, even though I've drawn a couple of extra stuff. We've got this 1 by 1 shape. That stands for constants, and if we put a lot of them together, I've still got that 1 by 1 shape in there. I've just got 1, 2, 3, 4, 5 of them. When I push them together, I get a number different than 1, and it looks like a rectangle. If I don't know what that is, I still make it look like a rectangle, and we end up with this rectangle here that we call x. And here's an example of 3x. And if I did 7x, I would have 7 of these rectangles put together. All right? And then I have my third shape right here where I've got a square, which is x times x. So this represents my units. This represents my x to the first power. This represents my x to the second power. You say, well, what about x to the third power? All right, I'm going to have to draw this three-dimensionally because x to the third power means cube. So I'll try to draw it. I might have to stand over here. Might need to go a little bit further than that. And I'm drawing it kind of oblique. It's not going to be perfect. But this now looks like a block, but it's a cube. From here to here, from here to here, from here to here, that's x. From here to here, here to here, here to here, that's also x. And from here to here, here to here, here to here, that's also x. So this whole thing up here, again, we don't have area now because now we've got 3 dimensions, 1, 2, 3 different directions to go. Now we say that the volume is x to the third power. Move that up so you can see it. So what we're going to do is when we add like terms, that phrase again, like terms, we're going to add the little squares together. We're going to add the rectangles together. We're going to add these bigger squares together that are x times x. We're going to add these cubes together. We're just going to find out how many of these we have, how many of these we have, how many of these we have, and how many of those we have. Keeping in mind that sometimes you have a positive number of them, and also we have negative. That's where the geometry part kind of falls apart, because you don't have such thing as negative area. Okay, but we can kind of pretend in terms of like negative means I'm going to take it away, like we used to say subtraction, take it away. Now you're probably wondering, even if you followed along with all this and this is making sense, you're probably wondering, what about higher exponents, x to the 4th power, x to the 5th power, x to the 17th power? That's where the geometry kind of falls apart also. I'm not a physicist, but the 4th dimension is time. So what actually happens is with x to the fourth, I believe, is that you actually start out with a point, it grows, and then it shrinks back down to a point. That's x to the 4th power. Higher degrees than that gets a little complicated. But I think we've got enough to be able to do some algebra. So now, I know that when I was just talking about this, I used x. The letter that we use does not matter. The only thing to keep in mind is that if you're using different letters in the same problem, they represent different measurements. And we can only add or subtract things that have the same size. So here's my m to the 3rd power. That looks like this cube, except instead of it being x, it's going to be m. So this is a cube. Geometrically speaking, it's a cube. This is my square. And again, this is more cubes. And you don't have to write this every time. I'm doing this to explain. So I've got 15 of these cubes. Do I try to add them to the squares? No, these are not the same shape, so I cannot add them together. So if this was the only part of the problem, I would leave it, because there's nothing more I can do. Those are not what we say like terms. They're not the same geometric shape. But let's keep going. Looks like I've got cubes here and cubes here. If I've got 15 of these and 2 of these, all together I have 17 of these cubes that are m by m by m, whatever m is. What do I do with the 6m squared? I can't get rid of it, but I also cannot do anything else with it. So that's my simplified form. I added 15m to the 3rd power plus 2m to the 3rd power. The 6m to the 2nd power stays, but I don't do anything with it. Let's look at this one. So here's a square, Here's these little squares. So this right here, 3x squared, means I've got 3 of those. 5 means I've got this. That is not the same as that. These little squares are not the same as the big squares. So I cannot add these two together. They don't go together. They're not the same size. Here I've got these x to the second power. And of course, this is, like I said, this is where the geometry kind of falls apart. Because what do you mean by -7 of those x squares? All right, think of it like I've got 3, but someone's going to take away 7 of them. So I'll give that person 3 that I have, and I'm still going to owe them some. Right? We'll talk about that. But these two represent the big square. These two represent the little square. So I'm going to put these two together. 3 plus -7 is -4. So if someone takes away 7 of my x squared, and I only got 3, I still owe that person 4 of them. And of course the little squares, the 5 plus the 12, 5 plus 12 is 17. And that's where I stop. I don't try to put these two together. They're not the same shape. All right, for the third one, don't panic because of the decimals. Don't panic because of the decimals. I've got y to the 5th power, another y to the 5th power, and I've got x to the 5th power, and another y to the 5th power. I don't know what the geometric shape would be for y to the 5th power. All right, talk to the physics people. But I do know that y to the 5th power is not going to be the same as x to the 5th power, because y is not the same as x. So I'm going to put together all of my y to the 5th powers. This is 0.9 subtract 0.4 plus 1, because I have a hidden 1 in front of here. Now you can put these together any way that you want. You can go left to right like the pre-algebra teachers tell you to do, but something called the associative property says if you're going to add more than 2 things, it doesn't matter what the order is that you're going to do it. I'll go ahead and do it left to right because it seems like it'd be okay. 0.9 subtract 0.4 is 0.5. 0.5 plus 1 more is 1.5. And that's 1.5 y to the 5th powers. So now, again, this is where the algebra is a little bit stronger than the geometry that we're using to symbolize it. That's 1.5 of these things. Not a full. If we weren't using x to the 5th, it wouldn't be like a full square or full cube. So we only got part of it. So that's where it kind of falls apart a little bit, but still, the idea helps us understand it. What about the 0.5 x to the 5th? There are no more x to the 5ths here, so I just leave it. All right, finally, for the last one. This actually you can kind of think about. X times x would be x squared, and y is a different number. So if I think about this, I can actually draw it like this, where this is x. I get a different marker now. That's 2 markers I'm down. So you're thinking, but that doesn't look like a square. That's because I'm trying to draw it 3-dimensional. And then it actually is what we in geometry call a rectangular prism. So this is y. So it's not a cube. It's more like a box that's longer on one side. And like I said, we call it a rectangular prism. So I've got 2 of these, but then I'm going to take away 1. So now I only got 1 left. And then I'm going to take away my last one. So this is just a way of saying 0. The whole thing ends up being 0. But don't worry about the 0 part. I wish they'd pick different numbers when I was doing these examples. All right, so hopefully the idea is that there is a connection between the algebra part with this and the geometry, and maybe that might help you do a little bit better with understanding what are like terms, this phrase right here. And the big important part is knowing, not just knowing what I can combine, but also knowing when I cannot add things or subtract things. All right, we'll see you in the next video.